Hi everyone. In this video, I will switch to introduction module and I will discuss in detail the types of introduction the STKO is offering based on the OpenSees, and I'll discuss in detail what is the introduction and what is the purpose of introduction. So let's switch to the introduction module. But before going to introduction module, let's create some geometries so that we discuss them one by one. So let's go to geometry and select a point option here and define points. Let's switch to 3D. Okay, sorry. Let's define in y direction the points here. So create a point with the coordinates 0, and the end point will be 100. Sorry, the end point will be 100. So we can see now the 2 points are created here. So let's create another one, call it um, 50 0 0, and create another one, and this will be 50 0 100. And let's create a line at starting point at 100 0 0 and ending point of 100 0 100, and right click to deactivate it. Now let's go to the front view. So let's create another line, call it 150 0 0 is the starting point, and 150 0 and 100 is the ending point. Let's switch to 3D to see. Okay, I'm sorry. Anyways, let's recreate this by 150 0 0 as a starting point, and 150 0 100 as an ending point. So yeah, now let's go to the front view to discuss the detail interaction type. We have these points. We generated these points here. So let's discuss what's going on in the back end. Basically, there are three kinds of interactions that the STKO is offering in its modeling environment, and these are uh, node-to-node links. Uh, we have node to element link, and we have another one that is general link. So each and every one has its own significance, and based on the OpenSees provisions uh, for the complex structural interactions, understanding these three primary interaction types, that are node-to-node links, node-to-element links, and general links, is very important for effectively utilizing this capability using STKO. And if we break down this into a detailed manner, node-to-node links represent direct connection between two nodes in structural model, and they act as a, if we make it more simple, they act as a conduit for transferring forces and information and enabling the simulation of various structural elements such as truss elements. For example, if we are interested in modeling a span joint connection members that can only carry axial forces such as tension and compression, then this type of link is ideal for simulating the trusses and cables and tie rods in integrated structure, for example. Then another application, a practical application, is the cable element. For example, if we similar to truss element, uh, if we are only interested in modeling an element that is only able to handle tensile forces, then this node-to-node link is a best example for that. Third one is, for example, if you want to consider a rigid link, so this node-to-node link is an example for that. And these links physically maintain a fixed relative displacement between the connected nodes, especially making them act as a single rigid body. And this is useful for simulating rigid connection or enforcing specific geometry constraint. Um, Other than that, we have a very common technique that is used in structure analysis for soil structure interaction. So that is spring element. Sometimes you use spring element as well. These links introduce a linear and nonlinear force deformation relationship between the connected nodes, and they can model various behaviors like elastic supports, dampers, or soil structure interactions in detail. So this kind of node-to-node link is very important in this manner in the STKO. So there are some key considerations for node-to-node links, and those considerations are simplicity and efficiency for the node-to-node links, as these are very relatively simple to implement, and these are computationally efficient, which make them a good choice for basic connections. By basic I mean simple connections. Um, Also, if we are interested in discrete connections, so these node-to-node links are often used to model discrete connections like trusses, cables, and supports within the structure that I mentioned before. And it's also very simple based on the behavior customization. For example, the specific behavior depend on the chosen link type. If we consider truss, cable, rigid, spring, and its associated properties, such as stiffness, yield strength, and material model. So these links are very important, and its practical implementation is very necessary to understand. The second type is the node to element link. So the node to element links, basically this work as a single node which is connected to an element within the model. So if we consider first node as a master and second element node as a slave, then it will be same as the node to node link, but it will consider that as a geometry here. But we have the opportunity by node to element links that it connect multiple points or multiple edges to a single node. Sometimes, for example, if you are trying to connect a bolted, if you want to do a bolted connections, and you connect the stem of the bolt to the circular surface, then you can consider node to element links. So these links connect a single node to an element within the model, and they'll primarily serve to introduce additional constraint or effect on the element, such as support condition. For example, if you have studied the abacus documentation, it is kind of uh, tie constraint here. So in tie constraint, we constrain a surface or an edge to a reference point, and then apply the boundary conditions. So similar to that, the support conditions utilize these, and these links can be used to define axial support, define fixed supports, pin supports, or roller supports, a specific node within the element. And this allows for modeling various support configuration and boundary condition that depends on your choice if you are working with it. And sometimes we use mass loading, so applying concentrated mass load at a specific node of an element can be achieved through these links. And this helps simulate localized mass effects on dynamic responses, which is very important in OpenSees environment. So and they also can be modeled using anchor point, and these links can be used to connect element to rigid bodies or other fixed point in this model that we are studying here. And this is useful for modeling connections to foundation, abutments, or other external structures. So this node to element links, that is very, very important for geotechnical considerations. And you may notice in some research papers for soil pile structure interaction, and it's very important in that case. And similar to the node-to-node links, there are some key consideration for node-to-element links that we are able to get the targeted control. For example, they offer more control over specific nodes within an element compared to node-to-node links in allowing them for the localizing effect to control. And also for supported loading, they are commonly used for model support condition, concentrated loads, or anchor points, providing flexibility in defining structural constraints. And also for link type specificity, the specific behavior depends on the chosen link type, that is support, mass, and anchorage, and its associated properties. Uh, so this that is related to the node to element links. But remember that this is very important for geotechnical application. Other than that, you can also use them for your specific kind of interaction. For example, if you are simulating a line element with 3D connection, and you want to connect the end of that line element to the 3D connection, so in that case, then you can use this node to element link. After that, there is a another type, that is, if we look at here, general link. And the general link, similar to the previous two, these links offer the most versatile opportunities, and it can connect any number of nodes and elements within the model. So we have flexibility in selection of both master and slave surfaces. And the reason is they offer a powerful way to model complex interaction and introduce specialized behavior in the structures. Um for larger structures, if we are connected in a more wider range, and we are interested in that, then side structure interaction is an example. So if you are using general links, so these links can model the interaction between a structure and its underlying soil foundation. So by accounting for soil resistance and dynamic effects, they enable realistic simulation of foundation behavior and seismic responses. Other than that, contact mechanics is very important in finite element analysis, and general links can be used to model contact between different parts of structures. And this allows for analysis of friction, separation, and impact behavior, which is very important for understanding the joint behavior and energy dissipation. And also, for example, if you are interested in damage propagation, so these links can be used to model how damage spreads to the structures by taking into account material degradation and localized failure mechanism in the connection. And this provides a valuable insight into structural vulnerabilities in progressive collapse scenarios. So it's also preferable in some cases because of the nature of its complexity and power. It offers the most complex and versatile interaction capabilities in OpenSees STKO, and it's enabled the model of intricate structural behavior. And also, it has advanced application, and they are used to model complex interaction like cell structure interaction in detail, contact mechanics, and damage propagation, which are often required for detailed micro behavior structure analysis. And general link. Implementation require expertise, you should remember. So I think choosing the appropriate interaction type depends on the specific needs of your analysis. For simple connections and basic support condition, node to node or node to element links are often sufficient. However, for complex interactions and advanced behavior, general links offer the necessary flexibility and control uh, by achieving accurate and realistic simulation. So these information you can find them in the STKO PDF documentation uh, as well. There is no direct approach to this discussion in OpenSees documentation because that is command-based language only. However, you can uh, study it in your analysis purpose. Uh, Thanks to SDA software company, they have developed such a powerful and revolutionary toolkit in the form of STKO for OpenSeas to serve as an advanced graphical user interface that empowers a lot of scientists and researchers to harness the full power of OpenSeas. And without this, it's almost impossible because um, it's not almost impossible to work on the commands that are in the OpenSeas. Anyways, let's go to the first one by creating a new interaction, and let's call it node to node interaction. Here you can change the shader, which will show you the color and the line width and the point size of your interaction that you define. But it's not important. Uh, let's select the node to node links, and I have these 2 points. This is point 1 and point 2. So I will connect point 1 and point 2. You can look at here, right? So with node to node link, this is NTN, right? And in this NTN connection, the STKO is asking me for master geometry. So I will select the master geometry and then I will press enter to finalize this command, and then it will ask for the slave geometry. So this is the slave geometry. If I'm interested in connecting multiple points, still if I'm using the node to node connection, it will select the first point that I select. However, if I'm connecting it with node to elements, then I will be using this in such a manner that it will connect all the points here. So first let's demonstrate this by pressing enter. We will get an interaction here. So that's available in the modeling tree here now, right? And you can look at here. The second one is node to elements, right? So for node to elements, let's create a new one, and we can demonstrate this by making it uh, node to elements, right? And that will be something like this. I will select the node first and then press enter. Then I will select, let's suppose I select this one and this one. And make sure I mention these in detail. If these are not activated, you cannot do selection. However, if these are activated, then you can select them. When I press enter, I will look at the node to element connection here, which is visible here. Now, one thing is very important. For example, if you are trying to connect element to the node, then it will try to get the elements centroid and then connect it to the node here, and that's how it's works. For example, if I select node to element and I consider it like this, and I select the element first, right, and then press enter, and I select the node here and press enter. So you can see it's approximately based on the 1 point, which is not making any it's a representation here, but it will consider 1 point from it, right? And you can then edit them as well if you want to edit the slave selection here, and you selected it and press enter. It will be connected, but it does not make any sense here. If you swap them, this will be something like this. So now by swapping them, we can connect each type of elements based on its nature here. So with node to element links, we can select it in this way, right? So press enter, and this one, and press enter. So it is now connected in this way. Um, Other than that, let's just go to take a copy from this by this region, and by right click activate this command here to go to the node to the general link, right? And for the general link, as I mentioned in detail, this is a more sophisticated analysis way to consider. So but for general link, you can connect various edges in this way. So I mentioned that these are some of the details that are required, and we need to make sure what we are using makes sense. So this interaction is very important in the uh, finite element analysis. Sometimes understanding these interaction will make it difficult for you to have a better choice of which type of interaction you need. However, after some practice in some parametric studies, you will be able to get understanding on this whole process, that how you can achieve it. So in finite element analysis, interaction play a crucial role in accurately capturing the real world behavior that you are working with for the complex structures, and it represents the various ways different components within the model influence each others, and it's leading to a more realistic result. So some of the reasons for interaction finite element analysis, it's basically we are trying to model a real world connection and accounting for external influences, and we try to capture the complex material behavior, and we try to get benefit from utilizing interaction. So if we utilize these interaction, a more accurate analysis results will be obtained, because by accounting for interaction, finite element analysis can provide a more realistic representation of actual behavior of the structure under various loading conditions, and also improved understanding of structural performance is achieved. So studying the interactions between different components helps us to gain a valuable insight into the overall load distribution, stresses, concentration, and potential vulnerabilities of the structure. And also for the optimized design, interactions are very important. So just try to remember these points. Next target is to switch to the properties, and discussion of these properties is very important. Then we will try to go to the mesh, and after mesh, then we will discuss the uh, analysis procedure in writing input file, and this will conclude our whole preprocessor component in our analysis. So this is one by one discussion, and then after that, if we understand all these purposes of the tools that are available in STKO, we can further do a lot of discussion on the post processor. And when the discussion on the post processor is done here, then we can kind of switch to a lot of more discussions in our analysis. So we have various kind of opportunities that the STQO is offered to us, and we are able to now get a more realistic response from the structure. So it's not difficult, and working with these is very easy. Just you have to focus your attention on it, and I believe if you master the STKO, you will approximately get up to 40 to 60% knowledge of gaining strength of OpenSees. The remaining need some study for the theoretical background in OpenSeas and doing some practical examples on OpenSeas just to get a better understanding of OpenSeas, and then you can implement this knowledge to model the real world connection or the research validation, all these processes that you are trying to achieve. So try to focus on these videos, try to study the STKO documentation, and I'll try to also discuss the MPC documentation and other details in this video series to just make it easier for the users to understand all these processes so that they can implement it in their research work. Thank you so much. Have a good day.